Welcome to the class 8, and in the last class we were formulating the problem of coordinating an upstream and a downstream circuit breaker. So, we will continue with that particular problem. Okay. So, we had circuit breaker 1 and 2, and the question was what do you mean by coordinating these two breakers. So, we discussed what should be the requirement, and the points that were discussed was requiring to the requirements of the individual breakers. Then the next thing that you need for doing the coordination is to actually you need to perform a fault analysis at the different zones in the bus and identify what is the range of fault currents that you could expect through the protective device, and what is the nominal current, and then you will decide on what would be the parameters that you would employ for your breaker to enable the appropriate coordination. Okay. So, we started with the data regarding the circuit breakers. So, if you look at the circuit breakers, we had mentioned that the circuit breakers definite time delay of 40 milliseconds or 2 cycles. It has extremely inverse characteristic, and reset time of 30 seconds, and we mentioned that the I square t for conductor in zone 1 is 2 into 10 to the power of 6 ampere square second, and for conductors in zone 2 it is 1 into 10 to the power of 6 ampere square second, and then you could calculate what is the A of requirement of CB1, and based on our previous discussion you can relate that to the I square t divided by I pickup square. In this case you needed an A less than 39.5 seconds for CB1, and A for CB2 we identified it should be less than 44.4 seconds, and then we decide to actually have breakers CB1 and CB2. So, it has P equal to 2, B equal to 0.04 seconds, and A is 30 seconds for CB1, which is less than 39.5. For CB2 your P and B is the same, your A you could select it to be say 35 seconds, and 35 is less than 44. Okay. So, next we will have to look at what are the fault conditions. So, if you have a fault in zone 1, your circuit breaker 1 has to operate. So, for circuit breaker 1, your trip time at IF max in zone 1 is now 30 divided by 1400 divided by 225, which is the pickup current for that particular breaker, minus 1 plus 0.04. So, this is 0.84 seconds. If you look at the trip time at your IF min, you can do the calculations, it will be 1.64 seconds. The current level is 1000 amps in this case. So, it is 30 divided by So, if there is a fault in zone 1, CB1 has to operate. For fault in zone 2, essentially circuit breaker 2 has to operate. So, for circuit breaker 2, your A is 35 divided by 1000. The pickup current for circuit breaker 2 is 150 amps. And if you look at your trip time at IF min, the IF min is 600 amps, pickup current of 150 amps, so at 1000 amps the circuit breaker 2 trips in 85 milliseconds, in at 600 amps it trips in 2.4 seconds. Okay. So, the next question is, if for some reason circuit breaker 2 does not operate and circuit breaker 1 backs up circuit breaker 2, then you can ask what is the required trip duration for circuit breaker 1 during the fault range in zone 2. So, CB1 in zone 2 is now 30 . If you look at now at the minimum current level, so if you look at now at the two current levels at 1000 amps, CB2 trips in in 0.85 seconds and CB1 trips in 1.64 seconds. So, CB2 should obviously trip earlier. If it does not trip, then CB1 acts at 1.64 seconds. If you look at 600 amps, CB2 trips in 2.37 and CB1 trips in 4.9 seconds. So, if you look at this case, you have a margin of about 1.64 minus 0.84 of 0.79 seconds, and here you have a margin of 4.9 minus 2.37 of 2.6 seconds. So, the margin is greater than 20 to 30% tolerances that might occur. So you may not have the nuisance strip problems of say breaker 1 for some reason operating before breaker 2 for a fault in zone 2. And if you can then calculate what would be the I square t level corresponding to the fault in zone 2 and breaker 2 failing to operate. Okay. So, if CB2 fails, your I square t is at 1000 amps, it is 1000 into 1.64 is 1.64 into 10 to the power of 6 is less than 2 into 10 to the power of 6. So, the fault does not cause damage in zone 1. So, the damage does not spread to zone 1. So, if you look at the other range of current, you have 600 square into 4.9 seconds equal to 1.78, which is also less than 2 into 10 to the power of 6 ampere square second. So, you might, due to the failure of circuit breaker 2, you might have some damage in zone 2, but the damage does not now propagate into zone 1. So, the next thing that you would have in this particular situation is we had identified 3 zones. So, zone 1, zone 2 and zone 3. What happens for a fault in zone 3? Ideally, we have not indicated what is the protective device that is used in zone 3. It could be a circuit breaker or it could be a fuse. The question is, will the breaker CB2 act as a backup, and if it is acting as a backup, what is the fault I square t that is happening in zone 2. Okay. So, if you look at fault in zone 3, the primary protection is the local protection, and CB2 is backup. And if you look at now your trip time for IF max in zone 3, you have 35 divided by and if you look at your trip time at IF min in zone 3, your current level is now 450 amps. And you could then calculate what your I square t level is. So, your I square t at 600 amps, that turns out to be 8.54 into 10 to the power of 6 or 10 to the power of 5, which is less than 1 into 10 to the power of 6. If you look at the 450 amp level, you get 8.9. So, again, in case there is a failure in the protection in its local zone, then the CB2 settings will not cause the fault to propagate into zone 2. Okay. So, there is backup protection. However, in many situations it may not be possible to apply to obtain all the possible conditions. You might have situations where if you look at the example that we have been looking at, the fault current levels are not overlapping. If you have overlapping ranges of fault current levels, you may not be able to achieve all the conditions of your coordination requirement. Also, you might have situations where your upstream source might have impedances that are varying over a wide range. You might have transformers that are switching in and out. You might have lines that might be tripping. So, the impedances might be varying over a wide range, and over that entire range it might not be possible to achieve the full coordination. So, you might not be able to meet all these requirements, but your objective is to try and meet as many as possible. Okay. So, the other thing that we did in this particular example is look at individual values of fault current levels and looked at the maximum, minimum, and looked at what the timing trip timings are of the breakers. Another way of looking at coordination is to plot your trip time versus current and see where the curve lies, and we will look at this, say, in the case of a fuse, and by looking at the position of the curve you can get a broader feel for is the coordination working or not. Is it possible for one device to trip before the other device? So, many times softwares that do the coordination calculations can actually give plots of time versus current coordination curves, which also give you a visual feel of whether the coordination is happening over a range of conditions. Okay. So, in the second situation we will look at case where you are coordinating, say, between two fuses, a upstream and a downstream fuse. So, in case of a circuit breaker you have the pickup current and the actual current flowing through the protective device. In case of the fuse, you have looking at the ratio between your actual current flowing through the fuse and the current required to melt the fuse. Okay. So, similar to what we defined for the circuit breaker, you could actually now define a ratio M, melt ratio, as your actual fuse current divided by so as long as the current is below this melt current, the fuse is not going to get damaged. Once you go above that particular melt current level, you have a possibility of the fuse melting, and the time required to melt would now depend on your value of the current that is flowing through the fuse. Okay. So, we can, in this particular case, again we can define, say, zone 1 and zone 2, and we can define what it means by coordination between fuse 1 and fuse 2. For example, if you have a fault in zone 1, fuse 1 is the device which needs to operate. By coordination, if you have a fault in zone 2, you want fuse 2 to melt without damaging fuse 1. Okay. So, that is essentially the requirement for a coordination between a upstream and a downstream fuse. So, you can now define in case of a upstream and downstream fuse, if you have a fault, say, in zone 2, then the fuse that is actually protecting is actually F2. So, F2 might be called the protecting fuse. And F1 is actually the protected fuse. F1 is actually protected by F2. And you want your protecting fuse to be below, in terms of your fault melt time versus current characteristics, you want it to be the curve to lie below that of the protected fuse. Okay. So, the protected fuse would typically have a larger I square T, and what you want to ensure is, if you take a typical component, you would have tolerance, you would have the minimum melt time and a maximum melt time. So, in this particular case, your solid lines might correspond to the minimum melt time required for the fuse to melt, and your dotted lines might correspond to the maximum melt time. So, what you want to ensure is that the your some k times your T min of your protected fuse in this case F1 is greater than your T max of your protecting fuse F2, and k is a number which is less than 1. So, for fault current ranges in zone 2, you want a condition like this to be satisfied. Say you could take k as say 70% or 75%. So, you want to ensure that with some margin you have sufficient distance between this particular point T max of F2 and T min of F1. Okay. So, I think that gives you a picture about what it takes to actually do coordination between upstream and a downstream fuse, and here you can see that the curve gives you a picture. So, this shows at one particular point the range of current that might be experienced by F1 might be a range somewhere like this. The range of current experienced by F2 might be a smaller range. So, you want to make sure that within its range this coordination is being achieved. Okay. So, next we will look at the case where you are trying to achieve coordination between say a recloser and a circuit breaker. Say you have an upstream recloser and then you have a circuit breaker downstream. So, your recloser might be sitting at the substation and your circuit breaker might be somewhere further down the downstream, and by a recloser it needn't just be the timing of trying to stay close for some time, then opening, staying, reclosing again, etc. The logic underlying the recloser might also have a circuit breaker characteristic. Okay. So, in addition to the recloser characteristic, there might be an underlying circuit breaker characteristic. So, the circuit breaker in this particular R can be coordinated with CB2 like what we have discussed previously. So, now we will focus on what the characteristic of the timing in terms of the cycling between the open and close of the recloser should be, so that you can coordinate between R and CB2. Okay. So, the first question is what you mean by coordination in this particular case. If you have a fault in zone 1, so obviously the device that need to protect that is your recloser. So, R has to clear faults in zone 1. Now, if you have a fault in zone 2, the question is that fault temporary or permanent? If you have a temporary fault in zone 2, then it can be cleared by the recloser by its recloser action. Okay. But if you have a permanent fault in zone 2, you want CB2 to open before your recloser locks open. Okay. So, if you have a fault in zone 2, CB2 would open, then during the next reclose cycle your zone 1 would go back to normal operation, and it would continue with this particular breaker being open and the section in zone 1 having its normal power feed. Okay. So, if you look at then what the logic in the recloser is, if the current in the recloser goes above some particular threshold value, it will open. Okay. So, once it opens, the current goes down to 0, it will wait for some duration and then it will close again. Okay. So, after it recloses, it will see whether its current is still going above the threshold, and then it will go through such cycles of say closing for say n cycles. After n cycles, if the current is still above the threshold, then it stays locked open. Okay. So, in terms of logic, it is a fairly simple and straightforward logic in terms of what the recloser would do. Okay. So, if you look at the recloser logic, if IRMS through the recloser is greater than I some threshold. So, 1 it opens, it waits for some time, then it recloses, then if I RMS So, depending on what the n is, you can have 2 cycles, 3 cycles, number of cycles of the recloser. If So, with this logic, we will make use of the same data for say zone 1 and zone 2, and look at an example of what can be done when you have a upstream recloser and a downstream circuit breaker. Okay. So, we will look at the example where say the recloser, if you say you have a fault happening at some particular point of time, for a short duration the current level goes high, the duration T naught we have taken as 0.1 seconds, then it opens for a duration of 5 seconds, then it recloses now for 0.7 seconds. If the current level stays high again for in this duration, it opens again for 5 seconds. So, after 5 seconds it try reclosing a second time, and there it stays closed for 3 seconds. If the current is continuing to be above your threshold level even at the end of this particular 3 seconds, then it will lock open. Okay. If the current say came down at some point of time before this 3 seconds ended, then essentially the recloser would go back to normal operation, because it would not lock open, it would go back to the normal conditions. Okay. So, that is essentially the logic. So, we will take these as the numbers in our example for the recloser. for circuit breaker 2 we will use the same parameters as we had in our CB circuit breaker to circuit breaker coordination example, and we will look at the situation when you have faults in zone 2. So, what is shown over here is an example of fault in zone 1. It tried a permanent fault in zone 1, it tried 2 reclose cycles and it just locked open at the end of it. Okay. So, the current came down to 0 and stayed 0 at the end of such a situation. So, if you look at zone 2 fault, what your objective is make use of reclosing to clear temporary faults, and recloser So, we will look at what happens in this particular situation when you have fault current in the maximum and minimum current in that particular range in this particular example. Okay. So, at 1000 amps, which is the maximum fault current level in zone 2, you have your trip time of your circuit breaker is 0.85 seconds, and if you look at now your T naught duration of 0.1 seconds, then this corresponds to the breaker advancing by 0.1 divided by 0.85, which corresponds to 11.8% of your trip time for the circuit breaker. So, it is about 11.8% to trip at that particular condition, and then you have actually the first off duration T off 1 of 5 seconds, and the 5 seconds in terms of the overall reset time for the circuit breaker, which is 30 seconds, it means that it is resetting by 16.67% of T reset. So, obviously, it is not going below 0, so it now resets back to 0. So, at the end of your cycle over here, at this particular point, your circuit breaker 2 is actually now fully reset. By the fault current level, it went up to 11.8%, it came down to 0, it is fully reset at this particular point of your operation of the recloser. Now, if you look at your next action, so if you look at your next action, if you look at your close duration 1 TC1 of 0.7 seconds, so that corresponds to 0.7 by 0.85 of your circuit breaker. So, it is actually about 82.8% of your trip time. So, in this particular case it is advanced to 82.8%, Then if you look at your second open duration T of 2 of 5 seconds, it is now 16.67%. So, if you look at your circuit breaker, so at the end of your second T of duration, so at this particular point over here, you are now about 66% of your trip level in your circuit breaker. Now, if you look at your closed duration 3 of 3 seconds, 3 seconds divided by 0.85 is 355%. So, obviously, it has tripped before the 3 seconds has ended. So, your actual trip time for your circuit breaker that corresponds to 100. So, it did not require 3 seconds, it tripped in 0.3 seconds in the second reclose cycle. Okay. So, at this particular condition, essentially zone 1 goes back to normal operation, because the current level returned back to the condition of the nominal loading of that particular zone, and what the recloser did was it made 2 attempts to clear a temporary fault in zone 2, and because it was permanent, it tripped the breaker before the recloser locked open. And if you look at the margin, you have 3 seconds minus 0.29 seconds, you have 2.7 seconds of margin at 1000 amps current level. Okay. So, next you could actually look at what happens at the lower current level, because you have to look at across the whole range. So, if you look at the current level of 600 amps, your trip time is of the breaker so you know your trip time at now your reduced current level at the minimum current level. So, if you look at now your T naught, in this case of 0.1 second, this corresponds to 4.2% of TTR. If you look at T off 1, of 5 seconds, it is 16.7% of T reset. So, again the breaker is fully reset at this particular point. If you look at now your reclose duration TC1 of 0.7 second, that corresponds to about 29% of your trip time, and if you look at your T off 2 of 5 seconds, which is 16%, your circuit breaker 2 at this particular point So, if you look at the point over here at the reduced fault current level, it is about 12.8% into tripping. So, that is the situation of the circuit breaker at that particular point, okay, of time. So, if you look at then the next duration of reclosing, which is for 3 seconds. So, if you look at TC3 equal to 3 seconds. So, this corresponds to 3 divided by 2.37 or 126% of trip time. So, again the circuit breaker is going to trip before it when it reaches 100%. So, it is going to trip definitely before the 3 second duration that you have. So, your actual tripping so if you look at you had 12.8% from your first reclose cycle. So, what remains in your second reclose cycle is actually 87.2, which is 100%. So, if you look at the corresponding time, you get of 2.1 seconds would be the time required for your breaker to trip. Okay. So, the margin that you have in this particular case is 3 seconds minus 2.1 or about 0.9 seconds of margin at the lower current level. So, you can see that the margin is reducing as the current level becomes lower and lower. So, at very low current levels your breaker needs more and more time to trip. So, at some level there is a possibility that you might actually cause a lockout before your breaker operates. So, one thing you could do is you could actually decide on what your threshold level for your recloser needs to be. So, if you look at your fault current in your zone 2 or further downstream, if you have a fault in zone 3 etc., your current level can come down below 600 amps. So, there is a possibility that at some reduced current level your recloser might actually lock open before the downstream device acts. So, one thing you could do is you could verify now through calculations at IF of 524 amps, your CB2 trip will coincide with R lockout. So, if your current level is above say 524 amps, then your CB2 would trip before the recloser operates, locks out. So, if you set your threshold current level for your recloser to be higher than 524 amps, then the recloser would not operate at the reduced current level, and ensuring that you do not have nuisance trips upstream because of reduced fault current levels that are occurring downstream. Okay. Though in typical protection coordination practice, you typically design the upstream protection before you decide on what you do for the downstream. In some of these situations, you will have to look at the entire situation to decide on what should be the settings, so that you do not have nuisance trips. Okay. So, another situation that you can potentially have is then looking at a situation where, say, you have a recloser which is sitting downstream and a fuse or a circuit breaker which is upstream. So, we will look at an example where you have an upstream fuse and a downstream recloser. It could be say a backup protection fuse operating with a downstream recloser, and then the question is, how do you then determine the coordination settings? What does it mean for coordination to be done in this particular case? So, obviously, in this case, again, if you have a fault in zone 1, it has to be cleared by fuse F1. Okay. If you have a temporary fault in zone 2, your recloser should clear the temporary fault by its reclose action. If you have a permanent fault in zone 2, then your fuse F1 should not get damaged, which means that your recloser should lock open before fuse F1 gets damaged. In the previous example, your recloser should not get locked open before your downstream circuit breaker operates. In this case, you want your recloser to lock open before your upstream fuse gets melted. Okay. So, we will look at this particular example in greater detail in the next class, and the main idea behind looking at these situations in a distribution system is that now if you are doing coordination of your protective devices in some particular manner, now if you add, say, a DG to one of these buses, what would be the new situation? What would be the new fault current level? What would be the changes that you would need in the system when you introduce the newer distributed generation device? And this is something that we will continue with in the discussion in the next class. We will look at the example of the upstream fuse and a downstream recloser. Okay. Thank you.